Hello everyone. Today I'm going to be looking at spread of the data in Chapter 2, Descriptive Statistics. This is the third part in the series of Chapter 2. First of all, I will recap some of the things done earlier, and then we will start with spread of the data. Now, in our descriptive statistics, we started with graphical summaries of the data set. We looked at what is the best way to represent a categorical data, and then we also look at how do we represent a quantitative data. For categorical data, pie charts and bar graphs are the best way. For quantitative data, histograms, stem and leaf plots, and dot plots are one of the best ways to represent it. Then after that, we started with numerical summaries, where we concentrated in the last session on Chapter 2 was on measures of center of data, mean, median, and mode. And in this video, we are going to be talking about measures of the spread of the data set, where we will be studying standard deviation, variance, range, and interquartile range. We will also study the empirical rule for a bell-shaped distribution. Remember, the bell-shaped distributions are the ones which we talked about earlier. They were the symmetric, shape kind of things. So these were symmetric distributions, like nice little, bell-shaped curves. So these are symmetric distributions, kind of this one we're looking at. And we're also going to finally look at z-scores. So let's start with measures of spread. Now, in measures of spread, helps us in summarizing how far a quantitative data or a variable is spread out, which basically simply means what is the distance between the data values in a data set. Either are the data values very close to each other, like this, like here, suppose I have a data set, I'm going to use a dot plot. So this is how so if you notice, the data values are very, very close to each other. Think of that. So this is one of the way we could look at this, or we could have a data set like this. Notice what's happening. The top one of this dot plot, basically the data values are very close to each other, whereas the bottom one over here is actually having the data values, but they're kind of spread out. So we're going to study a quantitative, what way we can find the spread and what does it give us, information and the formulas and all those things we look at. Now, the standard deviation, it measures the average distance of the data or this population or sample values from the mean. In a graphical form, it is like how spread the data values are. Notice, for a population standard deviation, the formula is given, this nice little formula where you see my cursor moving around. This one is the sample standard deviation, and we represent the sample standard deviation by a Greek symbol called sigma. So this is S-I-G-M-A. That's sigma. It's a notation for population standard deviation. So this is fixed, guys. For a sample standard deviation, it's the small letter S. And the formula is this, the one which I'm highlighting in blue. One important thing, and a nice thing for us, we are not going to use these formulas. We're going to use calculators, guys, to do our work. Okay? But the thing to keep in mind is this. In both the formulas, you see the mean present. And we also learned when we were doing about mean, median, mode, that mean is very sensitive to very large or very small data values which are present, like the outliers. So as the mean is present inside the formula for the standard deviation, it can be either sample or the population. The standard deviation will be also sensitive to these extreme data values present in the data set. Okay, now let's look at the other two measures of spread we are going to be studying. One is the range. It is the largest value minus the smallest value. Very simple to calculate. The other one is the interquartile range. In the interquartile range, we're looking at the 75th percentile minus the 25th percentile. I'll give you a nice little picture here. Suppose I have this nice little data set and I divide this data, all the data values are here. So we divide it into 4 equal, so parts like this one. When you go right in the top of the mound and down, this one is like 50% of the observations are to the left and 50% are to the right. And then you take the half of this one on the left hand side of this darker line, which, oh God, it's a little, this nice little darker line I have. So this one, and then 50% now. So this one, when we go on the left hand side, so this line, it means on the left hand side that 25% of the observations lie from this line. We will call this Q1 and we'll talk about this later on, but just to give you an idea, the middle one, this is which darker one, is Q2. It divides the data set in 2 equal parts. We talked about median, so that's Q2. And then the next line, so let me use actually colors for you guys. So this blue, so let's say this one, this whole part. So this one is like, this is Q3. That means this whole blue, 75% of the observations are lying on the left-hand side of Q3. And then the rest, this one, is 25% of the observations are above Q3. Okay. Now, for interquartile range, we're basically looking at the 75th percentile, that is Q3, minus Q1. So 25th percentile, this is the 25th percentile. Okay. Q3 is my 75th percentile. So you see this black lines which I'm making, this is called the interquartile range. So IQR is, guys, in between Q1 and Q3 is the interquartile range. Okay, now let's look at some examples. So here we're going to look at some of the students' hand spans in centimeter. These were my randomly picked up from one of my surveys I had done in my class. I have the hand spans for men. There are 11 of them, and 11 I picked from women. Now it says find the ranges of all the students, men and women together. The highest value notice is 23 and the smallest is a 17. So the difference between 23 and 17 gives us the range, which is 6. Now suppose if I had asked the question, what is the range for all the women student hand spans? Okay. So look at all these hand spans which are in the women. So the highest is 23, the lowest is 17. So it's the same as for all the students. So it's 23 minus 17, which is equal to a 6. Now let's look at the range for all the men students hand spans. So we look at the top row. The highest is again 23, but what is the lowest? A 19 or 18. So the range for all the men student hand spans is 23 minus 18, which is a 5. Okay. Now we will look at the sample standard deviations of all these students which are taken in the sample, and we'll also find the mean. As I said earlier, we're not going to be applying formulas. We're just simply going to use our calculators to do the work for us. I've written down the way to go about it, and I'm also going to show it to you here in the class, over here using a calculator. So guys, take your calculators out. In this one, what you're going to do is, as I said, the question says find the, notice what is it? It says find the mean and sample standard deviation of all the students taken in the sample, which is basically the handspans. So what we're going to do is we're going to plug in all these values from 23 till 18. So they're going to be 22 of them, okay, in our calculator. And then we will follow the formulas which are given over here. So go ahead, take your calculators out. And if there's something over there, please go ahead and if you find some values in L1, because that's where we're going to put these values, please clear the values and then go ahead and plug these values. So here I'm going to plug in. Right now it's already clean for me. So the values which I'm going to plug on over here, guys, are, so I'm going to keep this in front and I'm going to plug the values over here. So we are going to say 23, enter, 21, enter, then 20, enter. So I'm going to do somewhere like, okay guys, so, okay, 20, enter. So please guys, go ahead and start entering the values here too. 19, enter. So I have 23, 21, 20, 19, then 21, 22, now 2 times 23, 2 times 19, 1 times 18. So we've got all the 11 values here for the men folk, and now we're going to put the women students' handspans. So 19, 2 of them, 118, 117, 23, 3 18s, 2 19s, and an 18. So I'm just going to show it over here. So we're going to do, so we had 23, not 3 18s. A 19, 1 more 19, and then last 18. So see, you see this one? If you take the cursor, one more, it shows 22. So we're good to go. Now we just have to go ahead and find the mean and the standard deviation. So go ahead and click on Stat, guys. Now take your cursor to Calc. You already see the 1 is highlighted, and that's what we have to do. Click Enter. Now you need list L1. We do not need anything in frequency list. So please take the cursor if you have something written over there and delete it. Okay, and then take the cursor to Calculate and press Enter. Notice, it's giving us the sample mean to be 19.727, and the sample standard deviation, remember these are the sample values, the sample standard deviation is 1.956. Please do not look, look at the sigma. Sigma is representing the population, because I handfully picked up the samples of some students of my class, handspan, so I am going to be focusing on S of X. Oops. Okay. Let me get the okay. Okay. So notice we have mean here and we have SX. And when we look at what we also got, we have 19.727 and the sample standard deviation 1.956. This is pretty simple. The most important thing for us right now is the properties of the standard deviation. They are the same for a sample and population does not make any difference for us. Okay, so let's go over these 5 basic properties. The larger the standard deviation, the greater the variability of the data set. That's the meaning of it. Now, the standard deviation, either it can be sample or population, it measures the spread of the data. That is what the definition is. If the sample standard deviation is 0 or the population standard deviation is 0, that means there is no variability in the data set. Now, this basically means, like, let's look at a dot plot. If your values, all of them are stacked on top of each other. That's what this data set has no variation. They're all on top of one another. Now, if I have the variability, if you had more of them, so for example, let's look at this one. So if I have a data set, so these values are very close to each other, okay? So this is a standard deviation which is small in number. But if I start having more values here, this is the standard deviation which is going to be definitely larger than, very great in number or bigger value. Now, the things are the units of measurements for these standard deviations. When I talk of a standard deviation, I'm taking into account both the sample and the population guides. The units of measurement are the same for the original observations. If you talk of variance, variance basically is the square of the standard deviations. They have the same units, but they are not squared. And when we were talking about when we were looking at the definition of this standard deviation, we said that this is very sensitive to outliers. That means it is not resistant. A strong skewness, remember, if it is not resistant, that means if it is very sensitive, that means our data set is going to get skewed. A strong skewness or a few outliers can greatly change the values of these standard deviations. Now let's go ahead and practice some problems on standard deviations. Now, according to 2006 Human Development Report published by United Nations, the life expectancy of some of the countries are given. We're looking at countries from the Western Europe and countries from Africa. So the question is, which of the group, Western Europe or Africa, has the largest standard deviation in terms of life expectancies? Okay. There are many ways of solving the problem. One is when you look at the numbers, you look at the highest and the smallest, that also gives you an idea. We do not have to go ahead and plug in the values and get it, but just looking at it and figuring it out, okay? So what I'm going to do is, I'm going to first look at the highest and the lowest, and that automatically gives me an idea how spread the data set is. So let's look at this one. In Western Europe, we have 77, 78, 79, and 80. Notice, so if I make a dot plot, that all automatically will give me a nicer one. We have only 4 values. So I have 77, 78, 79, and 80. I have 2 77s, 3 78s, 2 79s, and 80, 2 80s. Notice they are so close to each other. And so clearly the standard deviation is definitely going to be very small because there is not much variation in the data set. On the other hand, let's look at Africa. The values are 37, 40, 41, 2 47s, 48, 55, 56, 57. Well, the smallest is 37, the largest is 57. This is a big difference, okay? So if I make a dot plot, let's make a dot plot here. I start with 37, then there's some difference is 40, 41 is close, then some more distance, 47, then closer is 48, then some more distance 55, and then 56 and 57. So let's just make a little dot plots here, 55, 56, 57, 148, 2 47s, then a 41, a 40, and a 37. Notice how far there is the spread by just looking at this data set. That automatically says, hey, the standard deviation for Africa is much more larger than Western Europe. So sometimes, guys, when you are doing your problems, you do not have to always have a calculator. The interpretation and of the concepts are very important. So when we see the word standard deviation, the first thing in your, oh, it's the variability. It is the spread of the data values. And then when we looked at Western Europe, we found the values were very, very close, 77 to 80, not much spread. Whereas when we look at Africa, there's a huge spread of the data set. So I don't have to go for my calculators. I just can make a little dot plot and say, hey. So the answer is that Africa has a larger standard deviation. I'm just going to write SD for standard deviation as compared to Western Europe. Okay. Now, if you want to practice your calculator skills, you can just plug it in and get the values. I can give you the answers here. So this is for you to practice. For Western Europe, the standard deviation, the little s, is 1.13. This is for you to practice, guys. For Africa, the standard deviation is 7.31. Notice this number definitely matches up with, there's a big difference in that there's a larger spread. And 1.13 is very small because those data values are very close to each other. Okay, let's start with empirical rule. Now, what is an empirical rule? Empirical rule says if we have a bell-shaped distribution, okay, then the population, mean and standard deviation, or the sample mean and sample standard deviation are, have these specific information in terms of how many observations lie within some 1 or 2 or 3 standard deviations of the mean. So the first one is, what we normally do is a real nice little picture. I'm just going to make a smaller version of this here. So this is my bell-shaped curve. Now remember, the mound and the horizontal line on the same when you draw as vertical lines. So right beneath the mound on the horizontal axis will be represented by the mean. Mu is the notation for the population mean, and little x bar is the notation for a sample mean. So it says this, that empirical rule says that one standard deviation of either side of the mean, okay? So when I am on either side of the mean, one standard deviation. So on the left, it is represented by mu minus sigma. On the right, it is mu plus sigma, or I can say it is x bar plus s. On the left-hand side, it can be x bar minus x. So within one standard deviation of the mean, 68% of the population is there. Okay. Now, so I'm going to just become, so 68%. Now, when we go 2 standard deviations on either side of the mean, so let's go 2 standard deviations on either side of the mean. So I'm going to say mu minus 2 sigma on the left-hand side and mu plus 2 sigma on the right-hand side. What it says is 95% of the population or the data values or the observations lie within 2 standard deviations of the mean. Then, there are 3 standard deviations on this side of the mean. So this one is mu plus 3 sigma. Gotta go here, very close here. So this is mu minus 3 sigma, or it can be x bar minus 3 sigma, 3s, or x bar plus 3x. So when we are going 3 standard deviations on either side of the mean, roughly 99% or 99.73% of the population or the data values or the observations lie within it. A very, very important rule for us. This is only applicable, guys, remember, if you have a bell-shaped distribution. So once again, a bell-shaped distribution only works with has an empirical rule which says that within 1 standard deviation of the mean, 68.27% of the possible observations lie. Within 2 standard deviations of the mean, 95.45% of the observations lie. I'm becoming very, very pedantic here. And 3 standard deviations of the mean, around 99.73%. So roughly 99% of observations lie within 3 standard deviations of the mean. Okay. Now let's do some examples based on what we just learned on empirical rules. It says a recent summary for the distribution of cigarette taxes and cents among the 50 states and Washington, D.C. in US reported that the sample mean is 73 and the sample standard deviation is 48. Remember, we're looking at cigarette taxes, okay? So that's a sample mean and sample standard deviation. Based on these values, we would like to know whether the distribution is bell-shaped or not. Okay, remember, if it is an empirical distribution, according to the empirical distribution, that 99% of the observations lie within 3 standard deviations of the mean. Okay, so what we do is we actually write down what are the values on either side of the mean. So the mean here is given to be x bar to be 73. Okay. Now, when we go 1 standard deviation of the right-hand side, that is x bar plus s, which is 73 plus 48. What are we going to get? So 73 plus 48 is going to give us 121. Okay, fine. These values are nice to work with. So then 2 standard deviations, we are getting it to be 73 plus 48 plus 48. 2 standard deviations. So it's going to be what? 169. Okay, that's fine as we go. 3 standard deviations, x bar plus 3s. We get 217. So on the right hand side, we have no issues. So let's go on the left hand side. X bar minus s, that is 1 standard deviation. We get 25. Okay. Now when we go 1 more 2 standard deviations, what's going to happen? So x bar minus 2s. Let's do that. Can we get a negative number? Standard deviation, remember, is the distance. It can never be negative. Because what we have also learned was standard deviation, guys, means spread of the data set, which says if the standard deviation was 0, that means there is no spread, which also is telling us that my standard deviation can never be negative. Do you see that here, guys? The minimum value for your standard deviation, guys, can only be 0. That means there is no variation. So this is not possible. So the minimum value, say, is 0. Now remember what happens in this scenario. According to the empirical rule, if it is working, then the mount, remember, is always on the mean. So if I draw a rough curve, what happens when I draw this? The right-hand side of the tail is being pulled. So this is right skewed distribution. It is not a normal distribution. Do you see that over here, guys? So it's very important that this empirical rule gives us a lot of information. So bell shape would mean we would have got 3 standard deviations on the left-hand side and 3 standard deviations on the right-hand side, and we would have got all the observations for a bell shape. But that's not possible because we know a standard deviation, the minimum value can be 0, which means there is no spread of the data set. And that's a very key point. And also key point is standard deviation cannot be negative. So because of all this, we have a right skewed distribution. Now let's talk about z-scores. Now, sometimes we would like to make a comparison, okay? And we would like to make comparison between different scenarios, different data sets. We have to be very careful because suppose if I'm making a comparison between a height of a woman and a man, and then just looking at the numbers, I say, oh, this is a person is tall, but you have to be also careful of the fact is the average height, you're comparing heights of men and women, 2 different data sets. But if we can get those data sets into a common ground and then make analysis, that's the right way to do it. And the statistics tells us that z-scores is that concept which helps us get us answers on it. So in order to make, so simply remember when we talk about z-scores, what we're saying is we get the different data sets on a same platform and then compare the values, and then analysis is the right way to make it. So what is the formula for a z-score? Z-score is simply x minus mu over sigma. So here I'm assuming my data set is a population. Remember, the population parameters are mean and standard deviation, which is a sigma. So this is the standardized version or a z-score of x. Okay, let's look at an example of what I was just talking about. Like if I am having a data set for heights of men and women, and I would like to make a comparison. So here the problem is the average height of men is 69 inches with a standard deviation of 2.8 inches. And an average height of a woman is 63.6 with a standard deviation of 2.5 inches. Guys, I'm only taking the analysis of a US population here. This is not the right one for the whole universe or for a different country. This was the one for the US population. Okay, now we are looking at the height of Michael Jordan and Rebecca Lobo. Now these two are very famous players, sports players, and we would like to make the comparison between their heights. So when I look at this, oh, Michael Jordan is 78 and Rebecca Lobo is 76. Oh, definitely Michael Jordan is taller. Be careful. The reason is Michael Jordan has to be compared because he's coming from the population of the men and Rebecca is coming from the population of women. 2 different data sets. Just because I look at the numbers and say, hey, Michael Jordan is taller, is not the right way of saying it. So we would really like to know which one is real taller because we have to look at the data sets they're coming from. So that means if I'm making the comparison between a woman's height and a man's height, to have the right answers, we have to go back and standardize the data set. And the way we do it is using z-scores. And we are given the average height of men and the average height of a woman and also the standard deviation and standard deviation of men and women respectively. So what we're going to do is we are going to standardize the heights of Jordan and Lobo relative to those of the genders they are coming from. So that will help us to make a comparison and it will be much more better. So let's look at Jordan's z-score. It's x minus mu over sigma, 78 minus 69, 2.8, 3.21. So compared to all the men height, it is just 3.21, whereas Lobo's score, z-score, tells us the z is x minus mu over sigma, 76 minus 63.6, that's the average mean for a woman's height divided by the standard deviation of a woman's height, 2.5, gives us 4.96. Now they are on the same platform. That tells us that Lobo's height is more, she is much more taller as compared to Michael Jordan. Okay, some facts about z-scores, guys. The mean of the z-score of a population is always 0. The z-scores fall between -3 and 3. That means -3 means 3 standard deviations to the left of the mean, and +3 means 3 standard deviations to the right of the mean. These z-scores never have units. For example, a body temperature of a healthy human child has a mean of 98.6 degree Fahrenheit, a standard deviation of 0.62 degree Fahrenheit. Suppose your child has a temperature of 101 degrees Fahrenheit. What should you do? Well, you're going to look at the z-score as compared to the rest of the healthy human children. So we put x minus mu over sigma, which is 101 minus 98.76 divided by 0.62, 3.87. Oh my gosh, it is beyond 3 standard deviations. Remember, z-scores between, so in other words, if you have 0, 1 standard deviation, 2 standard deviation, 3 standard deviations. To the right, -1 means 1 standard deviation to the left of the mean, -2 to the second. So this number, 3.87, is somewhere here. It's way beyond the 3 standard deviations to the right of the mean. Okay, this is the mean, guys, remember. So what is this step you do? You just go to the hospital with your child. One more, guys. Example we are going to do. This is the 2006 Energy Information Administration records per capita consumption for randomly picked 27 nations. We are given the energy values in millions of BTUs. Now that's the unit of measurement for energy consumption. They have a mean of 167.8 and a standard deviation of 72.8. And it's roughly bell-shaped. Now it automatically says it's a bell-shaped distribution. Roughly or a bell-shape basically means we can apply the empirical rule. That's what it means. Okay. Now, if Italy, which is one of the nations that has been picked up, has a value of 138.7, so we would like to know how many standard deviations from the mean it is. Okay. So what do? Italy's z-score is z is x minus mu over sigma, 138.7 minus 167.8. Divided by 72.8 gives me -0.40. So that means the Italy's z-score is 0.4 standard deviations below the mean. Okay. Whereas if US has a value of 334. So how many standard deviations from the mean is it? The US z-score is 334 minus 167.8 divided by 72.8, which is 2.28 standard deviations to the or above the mean or to the right of the mean. So if I want to draw a nice little, standard deviation, the bell-shaped curve here, it says roughly bell-shaped. So we can do like this. Remember, for the z-scores, that is, it is 0, 1, 2, and 3. So the US is 2.28, somewhere here. That's the US. Whereas Italy is, so this is -1, that means it is 1 standard deviation below the mean, -2, -3. Remember, we're looking at z-scores. So Italy is somewhere here. That's Italy. Okay? So that's how z-scores help us to make comparisons and analysis of a data set. Thank you.